about the differences, some of the symbols, and some of this kind of the early steps. If you're new to the trade or you've always struggled with schematics and connection diagrams, pictorial diagrams, any kind of diagram or electrical schematic, you are not alone. There are a lot of people who feel the same as you do. And even with this, I'm going to be using a very, very simple residential air conditioner. And this is not a pure ladder schematic. A ladder schematic has everything connected in between two lines that run down either side. I'm going to show that to you here, but I want to primarily show you the basic air conditioning circuit with the schematic diagram and the connection diagram. So the first thing is, whenever I look at a new diagram, I look at the whole thing. So I can, I want to see what all is in it. And I tend to focus on the notes and the legend first, just to see if there's anything that I need to know about this that's going to be special. These are all pretty standard things. Factory power wiring is a solid line. Factory control wiring is a lighter solid line. Field control wiring, dashed line, dashed line. So when you see dashed lines like these here, these are lines that you would have to actually add. So when you see these little dashes here, these are lines that you would be wiring in the field. And when you see solid lines, these would be lines that are inside the actual appliance. So if you see these dashed lines here, these are your high voltage lines that you're actually wiring in. And then if you go in here, component connection, field splice, this would be something that you actually make in the field with a wire nut. And so here you can see the Y wire coming up and connecting to a wire nut. And so that's where you're going to see these nuts are where you actually have to make a field connection. So even here, if you have to use an external power supply, you would have to connect that yourself. And that's what they're showing here. Because again, some of these things aren't necessarily factory installed. They're things that you would add on. And that's where reading the notes and the legend first can really help you. Also pay attention whenever you see these little stars here, because that means there's something more for you to look at. And then it has a bunch of nomenclature, which is just the abbreviations that are used. So CONT is contactor, capacitor, crankcase heater, you got a star. And if you see here, all these stars refer to may be factory installed. So that means it may be there from the factory, or it may not be, or it may be something that you add. So those are things that you want to pay attention to here, because this is sort of a universal diagram for a wide range of different Comfort Series carrier air conditioners. And so some of them may have them and some may not. And so crankcase heater may or may not have it. Crankcase heater switch may or may not. Compressor time delay may or may not. Discharge temperature switch, high pressure switch, indoor fan relay, that one will be there because you see there's no dot. Liquid line solenoid, low pressure switch, outdoor fan motor, so on and so forth. Another thing to look at here is it's going to refer to the NEC. Everything you wire in needs to be in accordance with the NEC and local codes for anything that you're adding in. Use copper conductors only. Use conductors suitable for at least 75 degrees Celsius, which is interesting because that excludes Romex. Or what is, we call it Romex, but NM, non-metallic cable. So technically we should not be using Romex to wire in this particular unit because that is only rated at 60 degrees Celsius. Connection for a typical cooling only thermostat. So what is this? Isn't a heat pump setup, and then it goes on through. I'm not going to read all of them, but you get the point. Those are things that you're going to want to read. So first off, let's talk about the difference between a connection diagram, often called a point-to-point diagram. In certain NATE trainings, RICS calls it a point-to-point diagram, and then a schematic diagram, and what the difference is. In a schematic diagram, everything is connected in between the two sides. So you have L1 coming in here, L2 coming in here, and then everything makes the connections in between L1 and L2 because that's how electrical circuit works. It actually finds a path. So there's a path between the two sides, and you don't have a circuit unless you have a path. And so you can see we have the dashed lines here. Dashed lines mean that we installed those wires. We have an equipment ground. Equipment ground is always going to have this little, lines that make up an inverted pyramid. That's what an equipment ground is going to look like. And so now let's go through the circuit. So we've got L1, we wired this in. We have a compressor contact here, and you can see it's not connected to the rest of the contactor that it goes with. It's just sort of out here all by itself. If you look down here, this is the 24 volt side of the circuit, and this comes from a separate external power supply, 24 volts, from the air handler. This is a condenser diagram, so that's why you don't show, like you would see in a lot of schematics, where you've got you've got L1 and L2, and then it comes down here into the bottom, and then you see the transformer, and then it goes to the low voltage, because this low voltage is coming from another power supply from the inside. As we know, our transformer is on the inside in a typical residential split system. And so this is what a transformer looks like, but we're only showing the 24 volt side. Normally you'd see the squiggles on the other side. That would be the input power to the transformer, but we're not showing that here. So this is our 24 volt side here, and this is our 240 volt high voltage side. And so we only show the contacts up on this side because we show them separate from the contactor, because this is a ladder schematic or a schematic style diagram. Whereas if you look over here at the connection diagram here on the left, you'll notice that the contactor has everything all together. You've got the coil, you've got the bar that goes across. This is only a single pole contactor they're showing here, so this is just a bar going across, and then you have the contacts over here. Now, one nice thing is these are numbered, and so you can reference that this contact here is referencing over here because you can see they have the same numbers. So we could actually talk about, say I was trying to help you over the phone, I could say look at connection point number 11 on the contactor, and you could either be looking here or here, and they're the same thing. So these are both showing, this connection diagram or point-to-point diagram is showing the same thing as the schematic diagram, just in a slightly different way. Over here they break everything up to make it easy for diagnosis. Over here they put it together so it's easier for identification. So you can identify this as a contactor. It looks a little bit more like a contactor. Like I said, even this isn't really a pure ladder schematic because it has some elements of a point-to-point diagram in it. They kind of try to keep things a little easier. All right, so now we go through this contactor. This is a normally open contact. How can you know? Because if you look at it, you can see that there's a gap in between these two contact points. This is sort of a universal symbol for a contact. I could show you the symbol separately on its own sheet, but I'm going to show that the reason why I'm using this is a real diagram that you're going to see in the field, and I'm just going to kind of teach you what all these mean as we go. So this is a contact. This is a normally open contact because it doesn't have a slash through it. If it were to have a slash through it, then that would be normally closed. You can see that over here on the start relay. This is a hard start kit start relay, and that is a normally closed contact. You see the slash that goes through it. So L1 is coming in here. You'll notice that this setup right here is connected on the line in. So you're going to have constant power going here to this little doohickey here. And what is this doohickey? This is the crankcase heater thermostat, CHS. If you go down here, crankcase heater switch. Now, why did I say it was a thermostat? Well, I know it's a thermostat because if you notice this little image here, you'll notice that it's got this little squiggle where it goes up and then over and then over and then up. That is a temperature sensing switch. So whenever you see this little kind of image where the line goes up and then over and then up and then over and then back up, this is a temperature sensing switch. And I can also tell that it is a normally closed, open on rise temperature sensing switch. So I know it's temperature sensing because of what it looks like down below the switch. So this is like a connection point here, and I can tell it's temperature sensing. And the fact that it's closed means that it's normally closed. So under normal circumstances, it's going to be closed. Usually that's with no power applied. And then if the temperature increases, it's going to open. These schematics, they're all designed to be read from left to right, like reading a book. So this is the permanent connection, and then this part here is the part that opens if it slides up and closes if it slides down, like it is right now. And so it's normally closed, open on rise, which means if the temperature increases, it's going to open the circuit and shut off this doohickey here. Now, what is this? This is a CH, crankcase heater. So if the temperature gets too high, it's going to shut off this crankcase heater. Now, we also notice it has the star. The star means that it may not be there. May be there, may not be there, right? If we look over here at the connection diagram, we see we've got the same thing, and it shows us that it's wired in exactly the same way. It's just different because we have L1 and L2 kind of here together, wiring into the contactor more like they are in the field, instead of having them separated. So if you look here, L1 is on one side, L2 is the other side. That's sort of the defining characteristic of a ladder schematic. That's what we generally call it. Whereas this is more the point-to-point connection diagram. Again, I'm just going to keep saying that so you get that in your head. All right, so now how does this work here? I've done a separate video on this, a video about the crankcase heaters. Actually, I didn't do a video on this one. I did a video on the capacitor type. But basically, without going into it, this crankcase heater will only work if the temperature is low enough that the switch is connected, so it hasn't risen and opened the circuit, and if this contactor is actually open. If this contactor is closed, there will not be a voltage drop between 11 and 21, and if there's no voltage drop between 11 and 21, there can be no current that moves through this circuit. If this is shut, if this switch is closed, there's going to be and I hate to say this because this is a overused term, but there's going to be a path of least resistance across this switch, and there's going to be no voltage drop across it, which means there's going to be no current through this crankcase heater. And so the only time this crankcase heater can energize and heat the compressor crankcase is if this contactor is open, meaning the system's off, and the temperature is low enough that the crankcase heater should kick on and this switch is closed. Now you go through the compressor and you see the compressor common is connected to L1. L1 connected to the compressor common through the compressor contactor. The only way that this compressor can come on is if this switch goes from normally open to energized and closed, so the slash. So it has got to get the slash across it, the path across the switch for the electrons to travel through and hit the compressor. You'll notice inside this compressor, there is a normally closed open on rise thermal switch. Again, you read it like a book. It's kind of hard to see because this is really, really small, but if the temperature were to rise, this switch would open, very much like this one here. You see it's the same sort of symbol. And so that's what a thermal overload is. It's a switch that breaks common. Common is not a winding. Common is just a point in between the windings of run and start, but it's got a thermal overload in there, and that's where you connect L1 in this case. So that shows you how that thermal overload is wired into the circuit. Pretty cool. Now if you go through the run winding, now it's going to go over and connect directly to L2, and you see the other side of this contactor, both sides are called 23. Why is that? Well, because it is a solid, if you look over here on the connection diagram on the other side, it is a solid bar across a single pole contactor. It's just like a wire. It's a hunk of brass, hunk of copper, something conductive, and it makes that path right across. So it's really the same. 23 is the same both top and bottom. It wouldn't matter if you took all these wires and connected them down here. 23 is 23 is 23. We use it as a convenience connection point. And so it goes through common, then run, and then connects to L2 over here. Now if you look at the other side, now it gets a little more complicated. We have the start winding, and the start winding is only connected to the circuit through a capacitor. And in this particular case, we've got, a 521 typical potential relay type of setup here. I'm not going to go through all of this. I talk a lot about capacitors, so I don't want to bore you with the details of how this all works. But just to show you some things here, we've got a coil. This coil is what brings out the capacitor, and so we have a path that goes through here. This is what actually takes enough back EMF from the motor and opens up this switch. But you can see this switch right here, this contact. We call it a contact when it's shown like this, where it's powered by a relay or a contactor. This is normally closed, so normally it's going to allow a path through, and we're going to have a potential difference across our start capacitor, and we're also going to have a potential difference across our start relay. We also have this little weird guy here, this ST, so let's go down and see what that is. ST is a start thermistor. Some people call these soft starts. That is incorrect. The correct name for these is a PTCR, a positive temperature coefficient resistor. It's a goofy looking little thing with wires hanging out of it. If you've ever seen one before, I've written articles about this. Just look up PTCR on HVACrschool.com and you'll find out more about that. But it's a form of start kit, and you'll notice that it has a star and this has a star. Hard start kit with a potential relay and start capacitor is a more effective method of starting than is the ST or PTCR type of start gear. Again, I'm not going to go into exactly how that's all wired, but the main thing to know is this is connected through to the other side of the circuit as well. All right, so what you'll notice is the C terminal on our capacitor here. See, it says C, H, C, F. If you looked on a dual run cap, which is what this is, you would see H is HERM. That's the full term for it here. Let's look over here and see if we can find that. There it is. Same thing over here. H, C, F, HERM, C, and fan. H, C, F. The C is actually fed from the other side of the contactor, from the side that feeds common to the compressor. I've talked about this a lot, but new guys get mixed up on this a lot. They see C here and they see C here, but you'll notice the C on the compressor is connected to L1, and the C on the capacitor is connected to L2. Those two C's do not mean the same thing. They're just both common points. In the case of the compressor, C is a common point between run and start windings. In the case of the run capacitor, C is a common point between the compressor run capacitor, and the condenser fan capacitor. Okay, I know it might be making this kind of confusing, but we're trying to keep it as simple as we can while giving the essentials here. But the main thing to know about capacitors is that you see this little symbol here where you have the straight line and then you have the curved line on the other side, straight line and curved line on the other side. That is the symbol for a capacitor. So whenever you see that, you know you're looking at a capacitor. Whenever you see a winding like this, you know you're looking at an inductive winding, a magnetic winding. So this is magnetic. When you see something like this, where it's got the more jaggedy peaks, like CH here, and then the start thermistor here, you see how those are jaggedy. That means that it produces light or heat. In this case, both of these produce heat, so they both get hot, and that's why they're jaggedy like that. They're not magnetic. Motors are magnetic, so they have the curves. Curve here in the start relay because it is a magnetic coil. Outside fan motor, same thing. We feed the common terminal on the outside fan motor with one side. What's interesting here, this does not show that it has a thermal overload, but an outdoor fan motor also has one of these in it. One of these little guys like you have in the compressor. They're just not showing it here, but it's the same basic thing. We've got our common terminal here. We've got our fan, which is our start winding going to our capacitor, and then we have our run winding going over here connecting to L2. And you'll notice that here our fan is connecting to one side of this bar, this solid bar on our contactor here, and then our compressor's connected to the other side. It doesn't matter, because when you have that solid bar on a single pole contactor, both sides are exactly the same. So now we get to this point right here, and this is kind of an interesting thing. The way that these are supposed to work is that when the pressure increases, this opens. It's normally closed. When the pressure increases, this opens. But when they labeled this diagram in the factory, they labeled them incorrectly. So what they did is they put the LPS over top of the HPS and the HPS over the LPS. So these two are switched. Because this is a low pressure switch, what should happen is it should open when the pressure falls, and it should close when the pressure rises, okay? So in this particular case, this is showing that it closes when the pressure falls. That would be a high pressure switch, and opens when the pressure rises. That would be a high pressure switch. This one should open when the pressure falls and close when the pressure rises. So that's just a little typo there. A lot of times these things don't get caught for many years because people aren't looking carefully at the actual diagram itself. And so now we go in here to a little logic gate, and then eventually we end up making connection to the contactor coil. Contactor coil is what then energizes the contactor relay points. And you can see these two are separated from each other on the schematic diagram. If you look over here, you can see they're connected to one another. So we've got the Y wire coming up here, and it goes up through, and then it energizes this coil, goes through the logic gate. This symbol right here, this little like Y upside down, that is a symbol that means a time delay. So it's showing you a time delay. This is essentially just a little board, a little time delay board. If you look here, CTD, compressor time delay. That's all this is really doing is the logic in the board is creating the timer, just a little circuit board, and then that's allowing it to travel through and bring on the compressor contactor so you don't have short cycling. This right here is a liquid line solenoid. It's powered by Y. That would be fairly rare, but it would be something that you could run into from time to time. Liquid line solenoid valve, and then you have an indoor fan relay that would be powered by G. That's all on the inside. We don't actually have any of the inside here. If you look over on this side here, because over here we don't have any of the blower side, but if you look over here, you can see we've got G that powers a coil. It's a magnetic coil, and then it energizes this contact that brings on the indoor blower motor. And you can see it doesn't show that because that's all on the inside, and this diagram is only for the outside. Again, we got the external power supply, which is the transformer, that's also inside. And then we have our R that we've already talked about. This comes from our external power supply, and we're connecting that on the inside. This is wired up like a basic straight cool thermostat like we talked about. This is not a heat pump. If you have a heat pump, then you'd have the reversing valve, and you'd have the defrost board, and you'd have all of that as well. The biggest things to know are these symbols have meanings. Every symbol has a meaning, and it will help you understand how the system is operating. You can even catch some manufacturer mistakes sometimes. So hopefully that helps. Connection diagram, everything is shown in more like the position that it is, and in a more complicated system, it's very helpful to locate a component inside of the unit, but the schematic diagram for diagnosis and tracing out a circuit is really the way to go. This is an example of another very simple ladder schematic that's more like what you're going to see in more complex units. I'm not going to show you like a full big commercial roof tap package unit or anything, but this gives you an idea of what you're looking at, where everything is connected in between L1 and L2. You're really tracing across from one side to the other. So you can see this here, this G light is going to be on all the time. We have C, which is a compressor contactor. C on the other side, this is a 2-pole contactor. And so you kind of trace your way through the circuit. All right, so I hope that's helpful for you. Just a quick introduction to schematics. Oh, one other thing. I didn't say this, but this is what a iron core transformer looks like. I think I may have mentioned that, but that's another one you're going to see a lot out there in the field. So transformers, contacts, inductive coils, heaters, capacitors, switches normally closed. We have pressure activated switches, these types right here with the bellows, and then also we've got temperature activated switches, a bunch of basics for you to get started with. When you get into the big stuff, you're going to be relying a lot more on the numbers and trying to trace them out by identifying the numbers in the actual equipment, but you should start small and work your way up, and it takes time. So it's not something you're going to be able to rush into. You're going to want to take it slow, work your way through it, and you'll find that as you go, you'll get better at it. I'm Brian with HVAC School. Thanks for watching.